Thanks, guys, for attending. It's a Thursday, so it's been a long haul, right? I would imagine it's like a epic journey here at reInvent. I think I've walked 50,000 steps a day all the way here. So I'm here to introduce Nauto, give you a view of what we've been doing in improving driving safety, with some focus on machine learning and our infrastructure for supporting machine learning, both on training and for inference. And I'm happy to receive feedback and answer questions toward the end. Presentation is probably going to be about 30 minutes or so, and should be plenty of time for questions or early exit to lunch for those that are hungry and can't wait to get out of here. So we'll start with that's for those who don't know how to spell Nauto. That's Nauto, and if you Google it, you get Naruto, Neuro, a whole bunch of other things. So unfortunate naming, but we've been a company around since 2015. We're a startup in Palo Alto, and I'll show a quick video pretty shortly about what we do. That's going to give you a pretty good synopsis on a 1 minute video about sort of the end-to-end solutions we provide to our customers around fleet safety. So already jumped quickly through the agenda, intros, couple of main components around our machine learning infrastructure, and then potentially next steps that we'll be exploring, and I'll actually love to get feedback and thinking whether we should be looking at something else. Slide on video and let's jump right in. Get out of that. Some of these graphics are not showing up properly, but well, let me try to voice it. As you can see, we see a strip of 400 plus fleets, 16 industries, and 400 million AI-powered processed video miles on the slides. So Nauto, as I mentioned, has been around since 2015. We're a 5-year startup, and we're a Series B company with investments from a number of well-known VCs. Our focus is enterprise. We build end-to-end AI solutions that really aim to improve driving safety. For enterprises especially, has significant liability footprint that wants to reduce that, and also just for general safety of vehicles on the roads, especially for segments that we work with: passenger delivery, service, passenger transport, service delivery. These vehicles operate all day in dense urban areas where their potential for impact, or especially negative impact, can be pretty high. So our solution being end-to-end, we make. Let's sort of jump right here. We saw a picture of the physical device, which is a small form factor device that goes typically installed behind rear view cameras in enterprise vehicles. If you have taken a taxi in Vegas, you most likely have seen our device. We have significant coverage in Las Vegas, especially during reInvent, CES. Our heat maps basically light up, and we get end-to-end coverage over town. A number of big metros inside. In the U.S., in Europe, and in Japan. One of our larger investors is SoftBank Vision Fund, and we operate through basically all of Japan. The graphics don't show that, but the slides will in the future. So what does Nauto AI enable? So these devices have cameras. So they're monocular cameras, 2 of them, one looking at the roads, One looking inside, looking at the driver and the passenger, right? So exteriorly or interiorly, we look at. You saw an example of distraction detection. So we detect distracted driving. Exteriorly, we look at tailgating, typical ADAS features. But and there's additional sort of interior looking at whether the driver's drowsy. It's how focused he was in driving, and coupling that with what we can perceive outside the car and the various sensors that are installed on these devices, we can make immediate decisions at the edge about whether they're performing a dangerous driving event. And when we do detect that, we provide in-cabin alerts, usually through audio, to correct that behavior. So for both distracted driving and tailgating, and depending on the severity of that of the violation, we change the audio tuning and making sure that we really correct that behavior. Once the models on the devices detect the fact there are dangerous events, especially in the case of the alert, we send that information to the cloud, which we operate. Then we operate a SaaS platform aimed to support fleet management to further improve driving safety through coaching, mostly through coaching and gamification techniques to help reduce that sort of risk, the risk measurements. I mentioned the sort of depersonalization. Obviously, we are aware that with these cameras, we're capturing private data, extremely private data, both for drivers and passengers, especially if you're in the vehicle. There is significant governance in place and techniques built out to depersonalize that data, both vision data that we can actually see of the person, as well as your sort of travel, your trip information is also de-anonymized. Based on, we're operating in Europe today. We're a Palo Alto-based company, so we're certainly in California. In both the privacy policies in terms of GDPR and CCPA all plays a pretty significant role. All the graphics are gone. Let's see if I can help it. So let me see if we can jump through this slide, because there's not that much things on here. This talks about sort of, it's a closed loop AI from cloud to edge. As we sort of discussed, the device themselves run, we have multiple GPUs, we have access to DSP, so we run deep learning algorithms, computer vision algorithms on the edge, right? So we have access to the frames, we have access to both vision frames and sensor frames, which are combined to make predictions about what's happening at the edge. That information is then sent to the cloud, which we continuously learn and improve our models, in addition to support any other types of product features. And then, because those devices are LTE connected, any improvement is immediately delivered back to the device. So that closed loop is what's keeping us, allowing us to quickly iterate as we start ramping up our deployments or different types of driving situations, different metros, and the models themselves continues to get better. Quick discussion on sort of ML infrastructure. So there's a lot of conversations, and obviously, Amazon, AWS has contributed significantly in sort of standardizing ML infrastructure. What we aim to do at Nauto is be as opinionated as possible about how we train models, right? How we train and validate and then run inference in the cloud, and it's certainly backed on the device as well. So this requires us to provide systematic controls and tooling to sort of the entire sort of machine learning model cycle, which is model building cycle, which is from a data management perspective, from a code management perspective, and also from a process perspective. Because the aim is we all want to build models. We want to quickly iterate on models, but in a process that's repeatable, right? some point building models if you can't actually repeat on why the model actually got there. So ultimately, the process is in place, the infrastructure is in place to ensure that the data sets, the training codes, the training infrastructure, the inference infrastructure is repeatable and flexible as possible. So high level how it works today. So we got devices are generating data. These are time series data with various types of telemetry, including video being a time series, sensors being various time sensors, IMU, GPS being time series. We annotate that data, just like if you're training models today, you know how the process works. We annotate that data with our internal annotation tool, and as well as third-party annotation providers like Ground Truth or any other providers that are out there. That data is then fused together in the cloud, right? So we basically go through a packaging process where the video sensors are aligned on the same time codes, the labels and annotation are aligned in that same time codes, and then that type of the annotation themselves, and then validated through models we actually run in the cloud, and then starts really the training process, which is about the preparation of ground truth data sets and feed that into a model training process. With same as on SageMaker, we use SageMaker and EC2 instances for training, and then we currently use ECS for all the model serving in the cloud today. ECS on GPU instances. And then we're actually in the process. I mean, some of this we'll talk about in the next steps is us adopting Elastic Inference as the Elastic Inference support gets more native in ECS. So some of the use cases we're looking to support, it's this convenient access to annotated data, more centralized, centralized and managed data sets that's easily accessible. Model training process that are repeatable, right? And then obviously once it's deployed, make the deployment easy, and then once it's deployed, you want to monitor it. And what we add is we add a human in the loop process for ensure that for supporting product features, but also for validating validating model performance. So talk a little bit about sort of how we prepare ground truth data sets today. And some of the goals here are listed, right? So the data sets themselves need to be immutable. So as if I was a machine learning a deep learning engineer, and I train my model version 2 on data set epoch 2, the epoch 2 data set can't change, right? So if I try to train that thing 10 days later, I need to be certain that I get the same data model back. So, and that's really what immutable means. And then it also needs to be efficient. I mean, how do we provide that immutability? Basically, how do you track sort of time series data or data that changes, whether slow or fast changing dimensions over time? Is you want to make sure you need to be able to capture full materialized data sets, and at the same time have flexibility to handle deltas, because for us, our deltas are significant, right? Where data is changing all the time. So, so that's really what the goal of sort of the ground truth data set preparation, the data set pipeline. It's a part of our overall data infrastructure that package all these pieces together. We leverage a number of open source tools. Data warehouse, data lakes on S3 it's a very commonly accepted practice now. We do that today, and then we feed that data lake with Kafka up front. We'll talk a little bit about the sort of the data flow a little bit later, but Kafka up front with running Spark and Presto and data stored on Parquet. So and one of the things we're looking into for achieving this kind of full plus differential is some of the things that you're probably hearing a little bit even in EMR talks today or the last couple sessions about is things like Apache Hudi or Databricks Delta Lake. These products are there for you to manage both full data sets and being able to provide sort of partial materialized views, or I mean not even materialized views, but basically data set abstractions that allow you to really look at data in time and get repeatable output. And obviously, data themselves has to make sense, right? It has to be, it it has to comply to some type of schema. And that schema, what you want to do is you want to be able to manage it centrally, but also enforce end to end. So that's something that we are looking to do. We're actually in the process of doing, which is using something like protobufs to ensure sort of end-to-end communication from device all the way to the cloud, right? And for those that happens to work in sort of the big data space, protobufs themselves are a native part of big data technology. So at some point, you have to convert from protobufs to Parquet. If you're working with Parquet's pieces, or Hive or Presto and some of these things, then you have to go through a conversion process. But protobufs gives us the ability to generate code that we can actually distribute to the rest of the teams, the folks that are working on device code, which is C++ or Java, working on the data side, which is Python or Scala, or our backend engineers all write Go code. So it's all those bindings are in place because protobufs provide us the ability to do that. So once you have the data set, you can train them. So why SageMaker, right? So I think we've gone through 5 years fairly similar paths a lot of ML startups do. Like we started with our own GPU boxes, right? We bought them because we felt like it would amortize over time, and it's much more scalable and cost-effective than sort of AWS cloud instances. And then we moved to the clouds, but before SageMaker, we were doing that with just self-managed EC2 instances, right? Instances maybe plus containers or something like that. And really, when SageMaker came to being, it's really a bit of a sort of a sea-changing piece of technology, right? Because it sort of allows us to scale. It sort of allows us to standardize and scale at the same time, which is really what's the capabilities that SageMaker provides, and it's obviously deeply integrated into AWS services. Some of those things are already highlighted here. SageMaker is one of the topics that's very popular, so I don't want to. This is not a SageMaker session necessarily, so I think you guys who work with SageMaker know some of the pieces. I do want to highlight sort of some pieces of sort of a training pipeline, what a training pipeline can look like, and this is sort of an example of our training pipeline for one of the models, right? We talk a little bit about dataset preparation up top. We talk, and then talking about what you do with that dataset, right? There's some pre-processing steps. For us, we deal with sensor data, video data, so that pre-processing step can be pretty significant depending on how we actually package this data together. And then from there, you have to figure out, what your test sets are, what your training sets are, what your validation sets are, and that's what your piece of technology provides you. And then it sort of starts. Then from there, you start your training, your validation process, and then eventually, once it's confirmed, you get to deploy them in the cloud. And we'll talk both on the training, a little bit on the training side, and some more on the deployment side on the next slide. So again, I don't think. I think this process, for the most part, is fairly standard if you're doing deep learning training. So some of the stuff the infrastructure team tries to do is try to provide standardization on top of like what SageMaker already provides, right? Which is to say, what are some of the things we can do to allow us, because of the fact that we use SageMaker, we use EC2 instances, we want to provide some common level abstraction that sort of packages our own internal learnings as well as taking advantage of what SageMaker can do. So things like custom containers, right? Like I think more probably, I don't know how many people. I think I'm not as a stats guy, but most people probably train on SageMaker use custom containers. So we have custom SageMaker containers for GPU and CPU for both TensorFlow and TensorFlow 2, and we use Airflow for orchestration. Some folks use, and especially if you're like Kubeflow folks. I don't know, anybody use Kubeflow, MLflow? Any of the guys here? Yeah. So all these things it's a way sort of to standardize what that pipeline can look like, right? So we use Airflow because we use Airflow already for like all of our big data stuff is all orchestrated through Airflow. So Airflow is basically our sort of orchestrator of choice on the training side. So it's enforcing basically the workflows and the pipelines, the data preparation, the model training, and all those pieces. And then on top of SageMaker APIs, we built Nauto SageMaker, for basically training, deployment, batch jobs. We'll also actually have it for serving as well. That's a bit of a work in progress. But all that is to provide standardization. And here's an example of what it looks like, right? So again, that's why sort of our containers allows us to do some of this stuff, which is basically bundle the Nauto SageMaker and a bunch of other dependencies as a part of the source code, as a part of the container, so you can be available locally without having to pull the stuff down and bootstrap. And you can see it looks like an estimator interface, right? I mean, so it's you pass in a Spark session, it's passing a SageMaker session. You invoke what the model training you actually want to run, and let's see, yeah, exactly. You say what instance size to use, how many of them. Some of the options are skipped here. What are the input modes? How many folks use SageMaker here? You do, okay. So do you guys use file or pipe for inputs? Do you use file mode or pipe mode for input? Mainly file mode, yeah. So there's this framework has sort of support for both file mode and pipe mode, but we all know the challenges of pipe mode, right? Which is like how do you randomize the data, how do you boost stuff, but there's some other sessions talk about how you can actually work around some of those challenges if you're doing pipe mode. You should seek them out because there's some good sessions out there about those things about how you really start your training. And then your hyperparameters are passed in, and then you basically run many of these with many hyperparameters, and you sort of just off you go, right? So just create an estimator, you start the training. That's that. Fairly standard. It's clean interfaces, pretty easy to get going. Happy to share more on these our learnings on here as well. So now you've got some trained models, and we sort of skip a couple pieces where this thing is outputting checkpoints, and you're hooking up tensor boards, you're evaluating these models on your own, and at some point these models are ready to go, right? So we have we have sort of an internal heuristic of our quote-unquote model zoo of how we actually keep models organized on S3, but ultimately the models themselves are stored on S3. And now we got to serve it. So we have a number of different serving needs where we do inferences in the cloud for product purposes. So in the beginning we talk about a significant part of what we do is private. The data we capture is private. Your faces are private. Your starting, ending location are private. We could use that information to figure out where you live, where you work, where you drop your kids. I mean, it's pretty dangerous stuff. So we run models to make sure that we know where they are, what those things are, and we obfuscate those things. And so some of these things is, for example, we run a facial detection model. After detection, we then blur your faces, right? Our customer says, especially when they have like passenger carry fleets, where it may be okay for you to capture a face of a driver, but it's not okay to capture faces of passengers, right? So because that's sensitive stuff, because they're not part of your employee. So we have support for that. So in those cases, we actually are, this particular slide is more not fitting that particular use case. It's more about the use cases of how we use the models to actually validate the device input. But there are some product cases that are not necessarily covered here. But here, this particular model serving, it's about using ECS to deploy models that we would be running on the device. But first, our development process requires those models to be deployed to the cloud. So we have streaming data coming in from the device. Some data is triggered by the device. Some is collected through research. And then our models are running in the clouds on those same data that our devices will be running on, perform validations. That information is then fed to human review, which is where some of the human in the loop comes in, and the human review is providing judgment. Let me quickly jump through this. We also have some slight issues. We'll fix that when we share this. Thank you. So, sorry, jumping a little bit quickly into the previous slide. I think in this previous slide was more further talking about how we're actually implementing the model inference in the cloud, and its integration into human in the loop. The number of SQS queues, we have basically incoming queues, outgoing queues, and task management and workflow management processes. The slide captures all that. Unfortunately, we don't have that here. We'll fix that a little bit later. I think if you rewind back to the beginning of the slide, looking at some of the use cases, one of the use cases is effortless model deployment, right? How does a scientist, after they finish to train the model, deploy their models into the cloud? As I mentioned, sort of, we use ECS today, and we use a bunch of SQS queues for pipelining this stuff. You know, if any of you have deployed to ECS, you say, okay, what do I have to do when I deploy to ECS? I have to go maybe create a service, right? ECS service. I have to create task definitions. I have to, because we use SQS queues for basically workflow management, then I have to create incoming queues, outgoing queues. We have automation for that. Automation is in CloudFormation. And as data scientists, you then have to go and write some CloudFormation code, write some Ansible code to glue all these pieces together, and then you know, let alone like training your models and write all the hooks into the models and funnel the data through. And especially with the type of data we have, you may have to do some additional pre-processing. So our typical process previously, and I do want to highlight our work on sort of this universal cloud models. Prior to universal cloud models, like, you know, give and take, you probably have to write about 1,000 lines of code or configuration to get a model deployed in the cloud. It's a lot to ask for a scientist, and it also takes multiple weeks to get something going, right? So we've moved to a piece. So basically, we moved to a model that's configuration driven, and it's both models and infrastructure, and it supports runtimes like TensorFlow, Keras, and Caffe. And here's an example of what that can potentially look like. So this is an example seatbelt detector model. We have a model that looks at whether you're wearing a seatbelt or not. It's interesting because people saying, like, why are you using computer vision to solve this problem? Like, why can't you say, like, if the seatbelt's clicked and I go LBD? And this is a pretty funny story, and it's a personal story, and it's not to pick out any region. But I was in a particular region traveling, I think it was somewhere in China. And the taxi driver had, like, this clip thing that just clips into the seatbelt holder. But he didn't have a seatbelt. He just has this clip. So the car stops beeping for him. So so I saw that. I was like, wow, this is pretty screwed up. So that's what this is built for, right? So this is basically built for, are you actually wearing, can we actually see you're wearing a seatbelt? So this is an example that would take, you either need to take images or video. So it doesn't need sensors, other type of sensor, it just needs imaging, right? So it's basically our interior camera can capture that. So this particular, it's sort of a descriptor to say, this is basically a 20-line, 30-line YAML file that is going to, after you sort of commit this and CI runs, you would have your seatbelt detector model running in the cloud, consuming our live devices. So things like, you know, some structure to define where the model is, some structure to define how we pre-process data, and then, you know, obviously what type of model is. In this case, this is a Keras model. We support TensorFlow frozen inference graphs, like I said, Caffe, and any type of Python model. And this is something that we're investing lots of resources on, and hopefully, you know, sort of will pay off for us, and maybe even something we would look to actually open up later. I think this is sort of the last meaty slide of mine. I'll jump to the next steps. No graphics again, great. No backgrounds. So on the platform side, so these are a few areas that we're actually looking at. You know, algorithms. We're actually deploying drowsiness detection today. You know, we've been doing that the last couple of weeks. You know, stop sign, traffic light detection for doing traffic violations. Things like obviously more forward collision warning on the ADAS features, and it means things. You know, people like, you know, Mobileye pioneer some of this stuff, and we're pretty interested in how we can do that in our ways. More platform adoption. I mean, I think Elastic Inference in ECS is. I don't think they announced this reinvent, but we're looking for more deeper integration of Elastic Inference into ECS at the container level. And obviously more use of SageMaker, other services, Ground Truth. We're working very closely with the Ground Truth team, the A2I team for doing human reviews, and then other data product use cases like Model Playground, where you can actually upload your own models to train on data that we have for both training and validation, and some light map and routing features. So I think that concludes the slides. And wait, this one has graphic. That looks good. But thank you. Any questions? Because the question is, do we support a full set of ADAS features, lane departures, forward collision? We are, I would say, we have models that do work on them. Not all of them have been productized yet.
What type of in-cabin behaviors are you able to detect?
So we fully productize all the various types of distraction events. So distraction when you're looking down, holding cell phone, when you're looking in direction while vehicles travel in a different direction, right? It's okay for you to look left if the car is going left, but it's different if you look somewhere else. Things like seatbelts, drowsiness we're deploying. And any number of, there's a number of algorithms that work, both vision-based, sound-based, and plus that, in addition to sort of the interactions. I think we're moving to a model where we're sort of, when we started, you sort of start with single sensor detection, right? Basically cameras or sensors. Then you sort of move to a multi-sensor detection where you have, cameras plus sensors. And then you bring in sort of third-party signals, right? Speed of travel, traffic violations, personal behavior, all that information is combining into building really a lot of these detection products. And I think we're beyond the sort of single sensor detection phase. We're multi-sensor, and we're bringing in human behavior as well. So all that is coming together from a product perspective.
What is the live map and the routing you mentioned there?
Yeah, and I think that's more about providing some live views about essentially when using not only traffic information but also using safety information about the routes that's for you for route planning. So in the case if you're saying I want to go from point A to point B, and Google Maps or some other provider gives you a particular route, that is based on traffic congestion, right? But also, even if I say our data can provide you that information in addition, in addition to traffic, but with also the safety track record of that particular route. So the segments you take, is it safe? Are you crossing stop signs or junctions or wherever there's prone to accidents? Things like that, so we can feed that into a planning system, a navigation system, or whatever, into making a not only a fast but also a safe route for you. What's that?
It's already available.
We're working on. I mean, it's something that we're actively working on. Appreciate it. Enjoy your lunch. Enjoy the rest of the conference.